Welcome back everyone. So in this video, we would now be resolving for this problem that is solved last video. But last video, we have solved for it using method number 1. So this time, once again, we will be resolving for it using method 2, which is the more or the faster approach. So once again, from our last video, for this problem, we have solved for an AS required equal to 1082.305. So let us now check if it is still the case. So again, for method number 2. So for method number 2, what we would be doing is that we will be making use of this formula for the coefficient of resisting moment. Then substitute it to this value of the rho required. So that is now equal to 0.85 times F prime C over Fy times 1 minus square root of 1 minus 2Rn divided by 0.85 F prime C. Okay, so from that, rewriting, so the coefficient of resisting moment that is now equal to the mu or the ultimate moment divided by V times B d squared. Okay, so for the reinforcement steel ratio, that is rho, this is now equal to 0.85 times F prime C divided by Fy times 1 minus the square root of 1 minus 2Rn divided by 0.85 F prime C. Okay, so in this situation, we only have 2 steps for step number 5. Unlike in the previous one, whereas this was our full solution. Okay, so this was what we did the last video. And for this video, we will be reducing it to just these two. But the main disadvantage of this is that, of course, you must memorize these formulas. Okay, so for the value of our resisting moment Rn, this is now equal to mu divided by phi b d squared, whereas mu, as per solved for last video, is equal to 126.893. Okay, so this is 126.893, but take note that this is in terms of kilonewtons meter or kilonewton meter, and from that we must multiply this by 1 million to be converted into Newton millimeter. Okay, so we will be dividing this by phi b d squared, but once again, for my phi here, I will be assuming that this is 0.9 because I want it to be tension control. So 0.9 times b. So in our problem here, where was our problem? So in our problem here, our BW is actually equal to 300 mm. So that is 300 mm times the depth. And the depth that we have solved for the last video is 342. So 342 mm. Quantity squared. Okay. So using our calculator, our coefficient of resisting moment is now equal to 126.893 times 10 raised to 6 divided by 0.9 times 300 times 342 quantity squared. So this is now equal to 4. So Rn is now equal to 4.018077. But instead of us listing this, I would just store this to A. So I will be storing this to A in my calculator. So this is now equal to, or I would just be shift storing it to A. Okay. So next up, for my rho, or for our rho required, so rho required. So this is now equal to 0.85 times F prime C, and F prime C, that is 28 divided by Fy of 420 times 1 minus square root of 1 minus twice Rn, so twice. And since I have already stored Rn to A, so this is now A divided by 0.85 times F prime C, and our F prime C is 28 once again. Okay, so from that, our rho required now is equal to, so looking at the calculator to your left, so that is 0.85 times 28 divided by 420 times the quantity of 1 minus the square root of 1 minus twice Rn, and our Rn is alpha A, divided by 0.85 times 28. So our answer here is, for my raw required, that is 0.01054868663. Okay, so from that, my AS required is now equal to, so just multiply raw required by B sub W times D. Okay, so substituting known values, so that is raw required. So I would just not write everything. Instead, I will just press answer in my calculator. So raw required times 300 times 342. Okay, so from that, I would just be multiplying this by 300 and 342. So as you can see that our AS required is now equal to 1082.295 millimeter squared. Okay, so this is now my AS required. And if we would be going back to our previous solution, where was that? So in our previous solution, this was, so not that. So in our previous solution here, so our AS required was 1082.305, and our answer now is 1082.295. We only have slight discrepancies because we had rounded our answers for A, okay? But essentially, as you can see in our calculator and in our previous solution, they are essentially the same. So it would be up to you which one you would be choosing in using. But then again, they are basically the same. Okay, so as you can see, that for our AS required here, that is 1082.295. And once again, if we are now to get the number of 16 pieces, rebars, so that is now equal to, so just divide this once again by pi over 4 times 16 squared. So we now have 5.383. But then again, we will be rounding this up to 6 pieces. Okay, so since we have rounded this up, let us check if it is still within the limit since we have rounded it up. So when we have rounded it up, the raw actual is now equal to, so let us get the total area of 6 pieces. So that is now equal to pi over 4 times 16 squared. So this is the area of 1 rebar times 6 divided by BWD, or 300 times 342. So this is now equal to, so looking at the calculator to your left, though, that is now pi over 4 times 16 squared times 6 divided by 300 by 342. So our raw actual is 0.0118. Okay, so looking at the limits, our limits would be as follows. So 0.033 and then 0.018. As you can see that in our answer below me, that is 0.0117. So it is greater than our raw min, and it is still less than raw max. So once again, that is now good. That is now for raw actual. But then again, in our steps, is this enough? Okay, so as you can see, it is 6 pieces, so meaning that it would now be oriented like this. Okay, so let me just rewrite our top dimension here as BW, and that is now equal to 300. And for our total depth, that was 400. So for our total depth, that is 400. Okay, so remembering our typical steps, so where is the typical steps? Our last step is for us to check for bar clear spacing. So, or clear bar spacing. And from that, guys, we are only solving for this dimension here, or the spacing itself. Okay, so how can we solve for it? So for the clear spacing SC, that is equal to the whole beam width, so B sub W, minus, so for the whole B sub W, we would be subtracting twice the concrete cover, since we have a concrete cover here and concrete cover here. After which, we would also be subtracting the bar diameters for stirrups, and those are 10 mm. So that is twice 10 mm since we also have two sides. Then after that, we will be subtracting 1, 2, 3, 4, 5, 6 times the bar diameter. So minus the number of bar diameter times the diameter of the bar itself. So with that, guys, if you would be subtracting those, the only thing left is this spaces here. So this space here, this space here, this space here, this space here, and this space here. So that is considered as 1. So from that, we will now be dividing it by 1, 2, 3, 4, and 5 in order for us to get the individual spacing of them. Okay? So from that, guys, so we would be dividing this by 5, or that is n minus 1 since we have 6 bars. Okay, so solving for this value, the spacing is now equal to, so looking at the calculator, that is 300. So this is 300 minus twice 40 mm minus twice 10 minus n dB. So by the way, instead of me writing 10 here, I would instead write dV. Okay. So from that, guys, NDB, and we have 6 number of rebars times dB, and dB is equal to 16 mm. So divided by 6 minus 1. So for our clear spacing, this is now equal to, looking at the calculator, so 300 minus 2 times 40 minus 2 times 10 minus, minus 6 times 16 divided by 6 minus 1. So our clear spacing is 20.8 mm. Okay, so from that, guys, we will be checking for its adequacy according to the code. So according to the code, guys, these are now our maximum limit. So that is 4/3 the diameter of the aggregates, or bar diameter, or 25 mm. Okay, so going back to this slide, so this must be greater than or equal to all of this. So 4/3 the diameter of the aggregates, the bar diameter, and 25 mm. Okay, so 4/3 diameter of the aggregates is basically, so since it is not given in the problem, I will just show you an example. That, for example, just so you know that for gravel used in reinforced concrete material, the most common bar diameter or diameter of aggregates is 3/4 inch. So if I am to convert this into mm, 3/4 of 25.4, that is actually 19.05. So just for our example, let us get 4/3 of 19.05. So from that, guys, so 4/3 times 19.05, that is now equal to 25.4, or basically 1 inch. And for dB, this is 16 mm. And for 25 mm, well, basically that is already 25 mm. So 25.4, 16, and then 25. As you can see, is this greater than equal to all of this? So actually, no. Though it is greater than 16 mm. But for these two, it would now fail. So it is not within the limit of the code. So even though theoretically speaking, 6 rebars can carry the required moment, according to the code, it is not allowed. Okay? So what can we do now? So since, as you can see, that we have solved for 6 bar diameters in one layer, in order for it to have a greater spacing, one way or one method that you can do is either you will be redesigning your beams in such a way that your beam width would be larger. So increase your beam width, or even increase your beam depth. Okay? So because if you would be increasing your beam depth, the required number of steel would also lessen. Or maybe instead of us making use of 16 mm, instead of us making use of 16 mm, you can actually use 20 mm. And if you would be using 20 mm as I think, so I think the number of diameter of rebars would now just be equal to 3 pieces or 4 pieces, I think. And from that, it would give you an adequate spacing. But what if, guys, like in this situation, we are stuck with 16 mm? So for example, that we are stuck with 16 mm, and as you can see, we cannot really change our BW because that is the limitation of the architect. And we are now to choose for the least depth possible. And for the least depth possible, that is already 400 mm. Okay, so another thing that we can do is instead of us orienting it in one layer, we can actually have two layers of 6 pieces. Though I have not solved for the spacing here yet, but as you can see, it is now a lot greater than before. Okay, so however, guys, if you would be doing it this way, take note that the value of D, so the value of your depth would now change. So earlier that is 342, but right now this is not 342 any longer. Okay? So if the spacing here, guys, is 25 mm. So suppose that you have two layers and the dimension of the spacing here is 25 mm. So our new depth, so D new, this is now equal to, so once again, the total depth of the beam is 400. So this is 400 minus, so again, for our depth here, it must be located at the centroid of the rebar. So it is, I mean, if you have oriented it in this manner, so meaning that the rebars is located exactly at the middle, okay? So from that, the centroid of the rebar is located exactly at the middle, okay? So from that, 400 minus the concrete cover of 40 minus board diameter of the shear reinforcement, that is 10, minus, so I will be subtracting the whole of this, so that is minus 16, minus half of 25, so 25 over 2. So for your D new, that is now equal to, so 400 minus 40 minus 10 minus 16 minus 12.5 or 25 over 2. So my D new is now equal to 3 to 1.5 mm. Okay, so recap, guys, that for our value of MU, that was, what was our value for MU once again? So for our value of MU, that is 128.893. Okay, so 128.893. So this is kilonewton meter. So let us try redesigning this once again in our second method. And that is by making use of Rn is equal to, so once again, Rn is equal to mu over phi b d squared. And our rho required is now equal to, what do you call that? So for our rho required, that is 0.85 times f prime c over fy times the quantity 1 minus square root of 1 minus 2Rn over 0.85 f prime c. Okay, so let us just substitute all of the things we know. So for our Rn, that is now once again equal to 128.893 kilonewton meter. But once again, please convert this into Newton millimeter first. So divided by phi of 0.9 times b. So again, this value of phi 0.9 here is an assumption since I want my beam to be greater than, I want my beam to be having tension controlled manner. So okay, so that is 0.9 times b, and my b once again is 300. So the only thing new here is the value of d. So our d new is 3 to 1.5. So 3 to 1.5 quantity squared. So for my Rn now, this is now equal to 128.893 times 10 raised to 6 divided by 0.9 times 300 times 3 to 1.5 quantity squared. So this is now equal to 4.619. And I will just once again store this to A. Okay, so from that, for my raw required, this is equal to 0.85 times f prime c, and our f prime c is 28 divided by fy of 420 times 1 minus the square root of 1 minus twice Rn, so I will just type A here, divided by 0.85 times 28. Okay, so that is 0.85 times 28 divided by 420 times 1 minus the square root of 1 minus 2a, so 2 alpha a, divided by 0.85 times 28. So our answer here is now equal to, so for the raw required, this is 0.01055. And from that, our AS required, this is now equal to, so that is raw required times BW times D. So this is now equal to 0.01055 times BW of 300 times depth of, where is the depth once again? The depth is 3 to 1.5, the new one. So this is now equal to, so times 300 times 3 to 1.5. So that is now 1017.421 millimeters squared. So for the number of 16 mm diameter rebar, so this is now equal to, so divide this by, so that is AS required divided by pi over 4 times 16 squared. So our answer here would be, so just divide that by, so just divide that by pi over 4 times 16 squared. So our answer here is 5.06. And thus, this would now be rounded up to 6 pieces. Okay, so since this did not change by our answer a while ago, still 6 pieces, so meaning that the raw, so for the raw, it is still within the limits. So if you would be comparing the raw of this, or the actual steel ratio, it is still the same, which is, where was that? So once again, our raw actual is still 0.0118 because we still have 6 pieces. It is just that this time, we will now be making use of 2 layers. Okay, so again, the 6 pieces of diameter rebars will now be distributed in 2 layers. And from that, let us now check if the spacing requirements is satisfied. So as you can see here, in one layer, we only have 3 pieces of diameter rebar. So from that, guys, for my SC or for my clear spacing, this is equal to BW steel minus twice the concrete cover minus twice the diameter of shear reinforcement minus the number of bars times the diameter of bars divided by n minus 1. So substituting known values, this is 300 minus twice the concrete cover of 40 minus twice the diameter of shear reinforcement of 10 minus the number of rebars. So this time, even though that we have computed for 6, in one layer, we only have 3 rebars. So 3 times 16 mm diameter rebars divided by the number of rebars of 3 minus 1. So from that, the clear spacing is now equal to 300 minus 2 times 40 minus 2 times 10 minus 3 times 16 divided by 2. So our answer here is 76 mm. So from that, guys, so for our limits, this must be greater than or equal to 4/3 of the diameter of aggregate. So previously, we have solved for this as 25.4 mm. And it must be greater than dB. And previously, we have already indicated that this is 16 mm. And also, aside from these two, it must also be greater than 25 mm. So from that, guys, 76 mm is greater than all of these, meaning that we will now be making use of this particular setting. So this is now the governing section. Okay, so there.